Inverses. Why to find inverses? Working in modular arithmetic, we often find inverses of number relative to an operation. There are two broad categories of inverses: additive inverse, which is relative to an additive operation; multiplicative inverse, relative to a multiplicative operation. Additive inverse. In Zn, two numbers a and b are additive inverses of each other if a plus b modulo n gives you 0. And in Zn, the additive inverse of a can be calculated as b equals n minus a. For example, the additive inverse of 4 in Z10 is 10 minus 4 equals 6. Note, each number has one and only one additive inverse. However, the inverse of the number may be the number itself. In modular arithmetic, each integer has an additive inverse. The sum of an integer and its additive inverse is congruent to 0 modulo n. Examples. Find all additive inverse pairs in Z10. The 6 pairs of additive inverses are 0, 0, 1, 9, 2, 8, 3, 7, 4, 6 and 5, 5. For example, 1 plus 9 modulo 10 gives us 0 and so on. Note, the additive inverse are reciprocal. If 6 is additive inverse of 4, then 4 is also the additive inverse of 6. Multiplicative inverse. In Zn, two numbers a and b are the multiplicative inverse of each other if a multiplied by b modulo n gives you 1. Note, in modular arithmetic, an integer may or may not have a multiplicative inverse. When it does, the product of the integer and its multiplicative inverse is congruent to 1 modulo n. Example 1. Find the multiplicative inverse of 8 in Z10. There is no multiplicative inverse because greatest common divisor of 10, 8 is equals 2 and not 1, which is against the rule. In other words, we cannot find any number between 0 and 9 such that when multiplied by 8, the result is congruent to 1. Example 2. Find all multiplicative inverses in Z10. There are only 3 pairs, 1, 1, 3, 7 and 9, 9. The numbers 0, 2, 4, 5, 6 and 8 do not have a multiplicative inverse. Using extended Euclidean algorithm to find multiplicative inverse. The following figure gives us an idea. The algorithm is shown in the figure B and the process is shown in the figure A. Here we can see that the number n is assigned to R1 and the number B, of which we need to find the multiplicative inverse, is assigned to R2. 0 is assigned to T1 and 1 is assigned to T2. The loop continues as R2 is greater than 0. Quotient is calculated as R1 divided by R2, that is in the first case, n divided by B. R is, that is our remainder, is calculated as R1 minus Q into R2. T is calculated as T1 minus Q into T2. And R1 is assigned R2, R2 is assigned R, T1 is assigned T2, T2 is assigned T. So this is how the algorithm works, and in process you can refer. Find the multiplicative inverse of 11 is Z26. The algorithm is same, the process is same. Here you can see we have assigned 26 to R1 and 11 to R2. The remainder that we have calculated is 4 and the quotient is 2. T1, T2, T. T is calculated as T1 minus Q into T2. It gives us minus 2 and so on. The greatest common divisor of 26, 11 is 1. The inverse of 11 is minus 7, or we can say 19. Find the inverses of 12 in Z26. The process is again same. The GCD of 26, 12 is 2. The inverse does not exist because we need to have the GCD equals 1. The addition and multiplication tables for Z4 and Z5 are given below. The blue one is the arithmetic mode 4 and the pink one is for arithmetic mode 5.